In this video, I'll talk about the heating curve. I'm going to use water as an example. This is the heating curve of water. First, let's look at the vertical axis, temperature in degrees Celsius. It depends on heat. So what's the horizontal axis? The relative heat energy in kilojoule. So what does this relative mean? In this graph, we arbitrarily choose liquid water at 0 degrees Celsius as the zero reference. And then if we add 7.5 kilojoule heat, so from here to here, all right, the temperature of this liquid water will increase from 0 to 100 degrees Celsius. From 0 to 7.5. So what if we abstract heat from liquid water? Okay, it's gonna freeze. If we extract about 6 kilojoule of heat from liquid water, it's gonna turn into ice completely. Over here, this is ice. What about the temperature change? There's no temperature change. From here, liquid water, to here, ice, the temperature is constant, 0 degrees Celsius. However, you can see heat changes from 0 to -6. That means water loses 6.0 kilojoule of heat. What if we keep extracting heat from ice? The temperature of ice will decrease. In this graph, it decreases from 0 to -100 degrees Celsius if we extract roughly 4 kilojoule of heat. Now at this point, you can see we have liquid water. This is liquid at 100 degrees Celsius. And then if this liquid water absorbs a total of 40.7 kilojoule of heat, it's gonna turn into gas gradually, right here. Right? From over here, this is roughly 7.5. Okay? And over here, I think this number is roughly 48. So you just take the difference. You get roughly 41 or 40.7 kilojoule per mole. From here, 7.5 to here, roughly 48. That's the amount of heat required to vaporize 1 mole of water. Again, it's 40.7 kilojoule. When liquid water at 100 degrees Celsius absorbs this huge amount of heat, again 40.7 kilojoule per mole, how does its temperature change? There's no change. The liquid water maintains at 100 degrees Celsius temperature. It's just converted gradually to gas. So from here to here, it's a constant temperature process. That's the so-called boiling point of water. Once all water is completely vaporized, now we can heat up the water vapor or the gas state of water from here to here, from 100 degrees Celsius to 200 degrees Celsius. So from here to here, roughly we need another 4 kilojoule of heat to increase the temperature of water vapor from 100 to 200 degrees Celsius. Now I'm going to give you several practice problems to work on and provide you with the answers as well. So I would encourage you to pause the video after seeing the practice problems and work on those yourself before watching the answers. The problems are related to the quantitative analysis of the amount of heat required to heat up ice from -100 degrees Celsius to 0 degrees Celsius. And also this amount of heat, how much heat is required to heat up liquid water from 0 degrees Celsius to 100 degrees Celsius. And also how much heat is required to heat up water vapor from 100 degrees Celsius to 200 degrees Celsius. And finally, in the end, how much heat is required to convert ice at negative 100 degrees Celsius all the way to water vapor at 200 degrees Celsius. By looking at this chart, you probably can take a guess of all those values. So for ice from negative 100 to 0, this is roughly 4 kilojoule. And then for ice to melt, roughly 6 kilojoule from here to here. Or you can just look at this number. To heat up the water from 0 to 100 degree, this is 0 here. From 0 to 100 degrees Celsius, we need roughly 7.5 kilojoule. And then 40.7 to vaporize the water. And finally, another 4 to increase the water vapor temperature from 100 to 200 degrees Celsius. So in total, I think this segment is roughly 5. So I think over here it's not marked, but it's negative 10 roughly. Over here it's roughly 52. So from negative 10 to 52, so I guess in total it's going to be roughly 62 kilojoule to heat up ice at negative 100 degrees Celsius. This is very cold. To water vapor at 200 degrees Celsius. This is very, very hot. All right. One more thing I want to mention. Under constant pressure, the amount of heat that flows into the system is equal to the enthalpy change of the system. Under the constant volume condition, however, the amount of heat is equal to the internal energy change of the system. So this is part of the chapter on thermochemistry. Again, constant pressure, heat equals enthalpy change. Constant volume, heat equals internal energy change. There's a difference because enthalpy is different from internal energy. H equals U plus PV. That's the definition of enthalpy. Again, enthalpy is defined to be the sum of internal energy and the product of PV. Now, 3 practice problems. Number 1, how much heat is required to heat up the liquid water from 0 to 100 degrees Celsius? And the specific heat of liquid water is 1 calorie per gram per degree Celsius. Well, you need to convert this calorie to joule first. Question number 2, how much heat is required to heat up ice from negative 100 to 0 degree Celsius without melting the ice? So it's going to be the solid state or solid phase throughout this heating process. The specific heat of ice is given to you. It's 2.1 joule per gram per Kelvin. So that means if you increase the temperature of ice by 1 Kelvin, you need 2.1 joule per gram of ice, or 21 joules of heat for 10 grams of ice, or 210 joules for 100 grams of ice. And then finally, how much heat is required to turn 1 mole ice at negative 100 degrees Celsius to water vapor at 200 degrees Celsius? Well, I need to give you the specific heat of water vapor, which is 2.0 joule per gram per Kelvin. Actually, this value is exactly the same as 2.0 joule per gram per degree Celsius. Remember, if we're talking about temperature change, 1 Kelvin is equal to 1 degree Celsius. Okay, that's the change of temperature. So if you change the temperature from 1 to 2 degrees Celsius, the change is 1 degree Celsius. It's also 1 Kelvin. Why? Because from 1 to 2 degrees Celsius, it's from 274 Kelvin to 275 Kelvin. So 275 minus 274, the difference is 1 Kelvin and also 1 degree Celsius. All right. So before I talk about the answers to these three practice problems, you may pause here and work on those problems yourself. Now answers. How much heat is required to heat up 1 mole liquid water from 0 to 100 degrees Celsius? The specific heat of liquid water is 1.0 calorie per gram degree Celsius. 1 calorie is 4.184 joule. This is by definition, and I know 1 mole water weighs 18 grams. More accurately, it's 18.02, but let's just do a rough calculation here. And then we have 18 grams of water. The temperature change is from 0 to 100, so I'm using the final temperature minus initial temperature to get the temperature change. This is the specific heat of liquid water. I converted calorie to joule. The result is 7,500 joule or 7.5 kilojoule. So if you look at the unit, degree Celsius and degree Celsius cancel, this gram and this gram cancel, so in the end the unit is joule. All right. Second question, how much heat is required to heat up 1 mole ice from negative 100 to 0 degrees Celsius without melting the ice? So right before the fusion process of the ice. And then I give you the specific heat of ice, which is 2.1 joule per gram per Kelvin. It's equivalent to 2.1 joule per gram per degree Celsius. Again, if we're talking about the temperature change, 1 Kelvin is 1 degree Celsius. Again, we just have the mass of 1 mole ice, 18 grams, times the temperature change. The temperature change is the final temperature minus the initial temperature. So from negative 100 to 0, we use 0 minus negative 100. The difference is going to be positive 100 degrees Celsius. And then multiply by the specific heat. So degree Celsius and degree Celsius cancel, gram and gram cancel, and then the answer is 3,800 joule or 3.8 kilojoule for this question. How much heat is required to turn 1 mole ice at negative 100 degrees Celsius to water vapor at 200 degrees Celsius? I need to give you the specific heat of water vapor. It's 2.0 joule per gram per Kelvin. So first, we need to compute the amount of heat to increase the temperature of water vapor from 100 degrees Celsius to 200 degrees Celsius. It's very simple. 1 mole of water vapor weighs 18 grams. What's the temperature change from 100 to 200? The temperature change is 100 degrees Celsius. When we heat up this water vapor from 100 to 200 degrees Celsius, the change is 100 degrees Celsius, or you can say 100 Kelvin, okay, because we're changing the temperature from 373 Kelvin to 473 Kelvin. This is the specific heat of water vapor. I just replaced Kelvin with degrees Celsius. Again, if we're talking about temperature change, 1 Kelvin is 1 degree Celsius. You cancel the units, you do the math, you get 3,600 joule, and this is equivalent to 3.6 kilojoule. All right, just to remind you, joule is the SI unit of energy, but very often for convenience, we use kilojoule. Now, from 1 mole ice at negative 100 degrees Celsius to water vapor at 200 degrees Celsius, how much heat do we need to provide to water? Well, it's very simple. It's over here, the addition of 5 numbers. Why 5? So first, we need to heat up this ice from negative 100 degrees Celsius to 0 degrees Celsius right before it melts. How much heat do we need? Well, we answered this here, 3.8 kilojoule. So we have this 3.8 here, kilojoule. And then at 0 degrees Celsius, we provide 6.0 kilojoule to melt the ice at the constant temperature, 0 degrees Celsius, 6.0. Again, the enthalpy of fusion of water is 6.0 kilojoule at 0 degrees Celsius. This is why we need this much heat to melt the ice. And then once the ice is melted, we have liquid water at 0 degrees Celsius. Now we're going to heat up this liquid water from 0 to 100 degrees Celsius right before it vaporizes. How much heat do we need? 7.5 kilojoule per mole. How do I know this? We did this right here. How much heat is required to heat up one mole liquid water from 0 to 100 degrees Celsius? We know the specific heat of liquid water. We just compute the amount of heat this way. The mass of water, the temperature change of water, the specific heat of water. We do the multiplication. It's 7.5. So we got 7.5 here. Okay, at this point we have liquid water at 100 degrees Celsius. Now we are gonna vaporize this water. How much heat do we need to vaporize 1 mole of water? 40.7 kilojoule per mole. Why? The enthalpy of vaporization of water is 40.7 kilojoule per mole at 100 degrees Celsius. So that's why I put 40.7 here. And then after vaporization, we have 1 mole water vapor at 100 degrees Celsius. We need to heat it up to 200 degrees Celsius. How much heat do we need? All right here, 3.6. So it's going to be 3.6 kilojoule per mole. And again, for convenience, we're using kilojoule here, not instead of joule. And then all 5 numbers are kilojoule. So in the end, we sum it up, we get 61.6 kilojoule. That's the answer. We need 61.6 kilojoule of heat to convert 1 mole ice at negative 100 degrees Celsius to water vapor at positive 200 degrees Celsius. Again, our answer is roughly 62 kilojoule. And if you look at the heating curve, it's from roughly negative 10 to positive 52. From negative 10, right here, negative 10, this is negative 5, 0, negative 5, so this is roughly negative 10. This is 45, this is 50, I think this is roughly 52. From negative 10 kilojoule to positive 52, the difference is 62, indicated by this heating curve of water. When this ice at negative 100 degrees Celsius turns into water vapor at 200 degrees Celsius, 62. So this is our result. Also roughly 62 kilojoule of heat.